Alright, so today we're going to continue our discussion on convergence, and we're going to be focusing on the idea of absolute convergence and conditional convergence. So let's just first talk about what absolute convergence is. So absolute convergence is, the definition of that is, if the series given by the absolute value of every term converges, then the series given by just the term, where we don't take the absolute value, converges absolutely. So all it is saying is that if we were to take the absolute value of every term in a infinite series, and we could prove that that new sequence given by the absolute value of every term converges, then we can say that our original series converges absolutely. And like a corollary of that is, if we're just given that this sequence converges, then that implies that our sequence without the absolute value also converges. And the proof for this is pretty easy, because let's say we have a sequence that consists of just the absolute value of every term in comparison to another sequence. Then we can, well, firstly, we know that the absolute value of a term, the negative of that, is always less than or equal to the actual term itself and the positive absolute value of that term, right? So this just comes from the definition of absolute values. And if we were to take this to the right hand side, we can rewrite this as 0 is less than or equal to the term plus the absolute value of that term, and that is less than or equal to twice the absolute value of that term. And this is just from us adding the absolute value of a to n on every side, right? And so if so if absolute if the sequence of given by the absolute value of a of n converges, then trivially twice that value also converges, because by this converging, we're just saying that this converges to some value L, and so multiplying that value by a constant will also be a finite value. So if we're given that the absolute value, or the infinite series given by the term, where each term is just the absolute value of a of n, converges, then 2 times absolute value of a of n, or an infinite series consisting of the terms of 2 times absolute value of a of n, also converges. And we know through the direct comparison test that if any series that takes on, or any infinite series that takes on values less than twice of absolute value of a of n should also converge. And we're given that, we're like over here, we're given that because of that, through the direct comparison test, so through direct comparison test, we know that a sequence given by the sum of a of n plus the absolute value of a of n converges, because like initially we're given that this converges, and that implies that any sequence that consists of twice of a of n converges, and we know that twice of the absolute value of a of n is always greater than or equal to a sequence that consists of a term that consists of the sum of a of n plus the absolute value of a of n. And we can split this into 2 separate sequences, one given by the sum of a of n and the other given by the sum of a of n. And we know that this summation over here is always less than or equal to the combined summation of like this combined summation series. And so we can apply the direct comparison test again, and because the direct comparison test gave us this top series converging, it also implies that the sum of just A of n converges, and that's what we proved over here. So that's just an aside to prove the fact that absolute convergence implies convergence. So the fact is absolute convergence implies convergence. So that's what we know about absolute convergence. And now, what's kind of contrary to absolute convergence is the idea of conditional convergence. And so, basically, conditional convergence is, well, first, I think to understand conditional convergence, the first thing, like, what this kind of implies that when we have something that are absolutely convergent, so implications of absolutely convergent series. The biggest implication is that if some series, the sum of A of n, converges absolutely, and if we rearrange the terms in the series to any arbitrary order, then the sum of B of n, which represents the new order, also converges absolutely, and to the same value. So what this is saying is, if we have a absolutely convergent series, we can rearrange the terms in those series and like reclassify that or notate that as another series, and both those series will converge, and they'll converge to the same value, which means that the order in which you sum up the different terms in a series does not affect both the value that we converge to as well as whether or not our series converges or not. So if, for example, if you have like 1 plus x squared plus x to the power 4 plus x to the power of 6, right, continues on, right? If we were to just like take the normal ordering and just sum like 1 plus x squared, then sum this, that converges to some value. But for some reason, if we decide to sum 1 plus x to the power 4, then we summed x to the power of 8, and then took the sum from x to the power of 2 to x to the power of 6. And like basically we took two sums of every other term, and then after we've taken those sums separately, we made like one full sum. That kind of changes the ordering in which we sum things up. But changing that ordering does not, in this case, you guys can look at like prove it yourselves as well, but does not in this case change the final value to what we converge to, and neither does it change the fact that we converge to a value. And because that's the case, we can call this series absolutely converging. Now there's other types of series that are called conditionally converging. And when a series is conditionally convergent, then, so if this series converges conditionally, then the terms can be rearranged to form a divergent series, but also rearranged to form a series that converges to any pre-assigned sum. And so this is very important. What it's saying is that when a series is conditionally convergent, we can somehow reorder the terms in which we sum up things. And because of the fact that we're reordering what terms we're going to sum, we can kind of make the summation converge to any sort of pre-assigned sum that we have. And that's the biggest difference between an absolutely convergent series and a conditionally convergent series. So given that, we kind of went over like what it takes to be an absolutely convergent series, where if we can prove that the absolute value of every term converges, then it's absolutely convergent. But if not, then we're not absolutely convergent. So if we can somehow prove, like through a test, that a series converges, but it does not converge absolutely, then we can say that it conditionally converges, and there's a chance that we can reorder things that allow it to converge to any possible value. And so, kind of like without getting into a specific test, to show an example of this, let's say we have the summation from n is equal to 1 to infinity of negative 1 to the power of n plus 1 divided by n. Let's show that we can rearrange the terms represented by the series to first form a divergent series. And then we'll show that it represents a convergent series. So one way we can kind of use this to form a divergent series is consider like us. Well, okay, so first, what does this series look like? I mean, the first term will be negative 1 to the second, which is 1 divided by 1. So 1 plus, and then we're just going to alternate our signs. So 1, so this should be plus, minus 1 over 2 plus 1 over 3 minus 1 over 4. So this is a alternating harmonic series. And the idea is, let's say that we start off in a way that we add positive terms to make our partial sum greater than 1. So if we do 1 plus 1/3, that'll have our partial sums greater than 1. Then we keep adding negative terms until our partial sums is less than 1. So minus 1/2, dot, dot, dot. Well, the first thing we do is like s of 1 is equal to this. So our partial sums is greater than 1. And then our s of 2 will make it so that we have s of 1 plus some other terms that make s of 2 less than negative 2. And then we continue this, where s of 3 will be greater than 3. S of 4 will be less than negative 4. And so if we like form this series in this way, which we can, because what we have over here is we have a series of alternating positives and negatives, where we can go positive, negative, positive, negative, and this does not really converge to a particular value. We can keep swinging it from one side to another. And so as s tends towards infinity, we basically have a method to continually increase, continually go towards the positive or negative, depending on like which term we are. So we are not converging to a specific value, and hence we have formed a way to make a divergent series. So that's like a property of conditional convergence, in that we can rearrange the terms in a way that we have divergence. If this was absolutely convergence, then any rearrangement would lead us to a convergence. But I've already shown you a way that we can rearrange the terms in which we don't have convergence. But because of the fact that this is conditionally convergent, there is, through a definition of conditionally convergence, it is possible to make a series that converges to pi. And how can we do this? Well, similar to how we crafted this divergence series, what we can do is start by adding positive terms. So sum is greater than pi. Then add terms add negative terms until sum is less than pi, and keep alternating. So keep alternating, but each time we overshoot pi in each direction, we are closer to pi. So in other words, let's say we want to converge at pi. The first time we're going to overshoot pi and like on the positive direction. Then we add negative terms until we overshoot pi in the negative direction. And then we keep flipping. But each time we overshoot by less and less, in a way that we're going to get closer and closer to pi itself once we overshoot. And in that case, in the limit, as we go towards the infinite sum, we're going to end up at pi because the way that we're overshooting is getting closer and closer to pi. And we can do that by rearranging the terms in a way that get us close and close to pi, because we have infinitely many terms to deal with, and so we can always kind of form a series in a way with these alternating positive negative terms for us to get arbitrarily close to pi. And that's one way to conditionally converge at pi. And I mean, you can kind of imagine that pi was just an arbitrary number. I could do that to craft a series that converges to 1,000 or like negative 1,000, right? So that's the property of conditional convergence, where if we were to rearrange these terms, we can either form like a diverging series. We could also converge to a specific value, which is something that you cannot do on an absolutely converging series, because absolute convergence implies that no matter what permutation of the series you have, you will converge to the same exact value. So that was the difference between conditional and absolute convergence.